First unit is actually the simplest and the shortest unit, but still it is going to have equal weightage when it comes to the examination. So it's going to take lesser time considering the topics which I need to cover in the first unit. So this is actually the topics of the unit one. It has got introduction, structure, operating system structure, system calls. Those are the topics to be covered. System boot is the last topic. We have already discussed the topics elaborately. So right now I'm just going to briefly mention the points. I'm not going in depth into the topics. It will be a brief discussion. Under the introduction topic, we have these headings: what operating systems do, operating system structure, operations, process management, memory management, storage management, and protection and security. Uh, these topics are in the first unit, they are all just highlighted, which are getting elaborated in the subsequent unit. So, except to the protection and security, this topic was actually included in the previous syllabus, but now when they reduce the number of credits from 4 to 3 to reduce the portion, this got removed. So we have covered everything else like process management, memory management, storage management. That is all discussed in various units. This is about what is an operating system, which is a program that acts as an intermediary between a user and a computer hardware. And these are the goals. So it is supposed to execute programs, make the computer system convenient, and use the computer hardware in an efficient manner. How do you define a OS? See, the operating system is very complex software since it encompasses a lot of different types of modules. So it's not precisely defined in a single statement. It can be seen in different perceptions. They are termed as views. So actually, this is a topic called views of an operating system. So these are different views. We can view the operating system simply as a resource allocator, in which case it is managing all the resources and allocating and deallocating the resources and avoiding the conflicts on resource access. And semaphore is an example for that. That is prevention of conflicts. Resource conflict is done with the mutual exclusion, which can be implemented using semaphore also. Another view is OS as a control program. So under the control program, we can look at it OS as one that controls the computer. That is, it controls the execution of programs, it controls the hardware, everything is under the supervision and control of the OS. So this is the classic definition, which is commonly mentioned. It is an interface between user and computer hardware, and there is one particular module of the operating system which is termed as the kernel. So the kernel is the collection of the most important or crucial modules of the operating system. So operating system has got a lot of different modules or functionalities, but not all of them are essential all the moment. So what is needed most of the time, they are made into a kernel, and the kernel is always loaded into the memory and it continues to run till the system is stopped. Other modules come and go as and when the need arises. So the kernel, the definition is important for you to know, to have a knowledge of the operating system. Next is the idea of multi-programming. So this is also very much you are familiar with. Multi-programming is the idea by which the CPU is switched among different processes. So without waiting for a process to complete in order to commence the execution of another process, there is a switching happening between one process to another process in the middle of the execution. This typically happens either when the current process go through IO operation, or when it makes a system call, or when it is interrupted, or when there is an exception happened to the process. So when such events happen, the current process is temporarily halted and a new process is sent to the CPU. And this may even happen due to round robin, that is time quantum or priority. So the variety of reasons are there which could trigger the transition of or the replacement of current process by another process. And one related terminology is preemption. So preemption is replacing or removing the current process in order to execute another process. If you include the time quantum into the multi-programming, it becomes a time sharing. So time sharing is same as multi-programming, but here there is also a time limit exercised or imposed on the execution. What is the advantage of time sharing over multi-programming is that time sharing makes the waiting time to be uniform. It does not allow the long process to monopolize the CPU, resulting in poor response time. So when time sharing is followed, every process has to wait for a equal time, and also every process gets equal share of the CPU. But the downside of time sharing or round robin is that it's going to result in poor turnaround time, because most of the process has to keep keep getting executed a number of cycles, so that could prolong the completion time of the processes. The next topic is operating system operations. Basically, computer is a interrupt-driven hardware. So we know the advantage of interrupt. This allows the operating system to initiate a work, and without waiting for completion of that, it can jump to some other work. So when the previous work gets completed, the OS is able to receive the interrupt, and then it comes back to that particular task. So this eliminates the idle time of the CPU. Even in an IO operation, the CPU is able to switch to another process, and when an interrupt received, it is able to recognize that the input is IO operation is over. And interrupts are also various types. You are aware of it, like software error or exception or trap. This is an error happened due to the mistake made in the current program's execution. It could be division by zero error, or it could be memory violation, or it could be illegal request, privileged instruction being attempted. So it could be any kind of error. So dual mode operation is a protection mechanism. So what is dual mode operation? It's a way to protect the computer. So how it is protecting is that the main memory is comprising of many things. It has the operating system, and it also has all other user processes. So when many entities stay together in a single memory, and when the memory is not physically divided for each of them, they are likely to interfere with each other. So the one program residing in a particular memory address may attempt to manipulate some other address, leading to the corruption of something else. It could even be the OS. So how do you prevent that? The basic idea is enforcement of two modes of operation. So user mode and clear mode, kernel mode, clearly separates the processes. So whenever the programs are running, that is user programs are running, the system is in user mode, and the moment some OS activity has to take place, the system turns into kernel mode. And this is indicated with the help of the mode bit, which is in the PSW. So program status word is a register which contains a mode bit through which the current mode is recognized. Under the kernel mode only, all the privileged instructions are executed. An example of when a kernel mode, when a switch from could happen from user mode to kernel mode is when an interrupt occurs, when a system call is made, when a trap has happened, when the time quantum gets over, when a high privilege process needs to execute. For all these reasons, the control of the system will be taken in by the operating system, and it will run itself. So whenever the operating system is present on the CPU, it is typically a kernel mode, and whenever the user program is running on the CPU, it must be a user mode. This is what I was explaining you. So the execution of user process takes place in the user mode, whereas the execution of the kernel mode happens in the kernel mode. The next is process management. So management of process is under the operating system's responsibility. But before that, what is a process? A process is any program which is in execution. So as long as a program is not being executed, it is just treated as a code, a source code, or I mean an object code or an application. But only when it is submitted to the operating system for execution, we call it as a process. So process is going to make use of the resources like CPU, memory, IO, files, and data. These are all various resources that the process could ask for. And the OS is responsible for fulfilling the requirements of the process. So it could create the process, terminate the process, schedule the process, supply all the resources for the process, provide synchronization among the processes, and also facilitate the communication among the processes. So all these tasks are coming under the process management of the OS. Next one is memory management. So memory is a resource of a computer, and it's a very limited resource. So there is only a small amount of memory available in any computer, and so it needs to be managed very efficiently. And also another limitation of the main memory is it's a volatile memory. So anything that is stored in the memory only exists for a small period of time until the computer uh, is not turned off. So it has to be loaded every time. And the operating system is responsible for the following activities, which is keeping track of which memory is currently being used and which are available. So it must maintain a table of the memory picture or memory status. Decide which process to load into memory when the memory becomes available. So this is precisely done by which one of the scheduler that is loading program from disk into memory is the responsibility of the long-term scheduler or the disk scheduler. And allocate and deallocate the memory as needed. So these are some highlights of the memory management, but we know very well that it also involves a lot of other complex aspects like partitioning of the memory and paging, segmentation, table maintaining the table. So there are other more detailed works being done by the OS. But in the first unit, we just get a hint of the responsibilities of the OS. Storage management or the secondary storage management. So here the OS provides a uniform logical view of information storage, and it abstracts the physical properties of the files. So when you store files, it may be stored in a hard disk or it may be stored in a SSD memory. So that should not the physical properties of the storage device should not affect the logical view of the files. So the operating system simplifies the complexities of the storage devices and makes a uniform provides a uniform view of the files that are stored in it, and that is done with the help of file management. So under file management, many activities happen: creating and deleting files, manipulation of files, mapping files into secondary storage, directory management. So there are many works done by the file under the file management, and that is explained in a separate unit. We have gone through that. So file management. Next one is mass storage management. This I think okay, disk scheduling is covered in that. So coming to IO subsystem, IO subsystem is the basic task of the OS is hiding the peculiarities of the hardware devices. So we have got a variety of IO devices, each have their own characteristics. So that should not affect the programmer. So programmer should be able to handle the devices in a uniform way without getting into the complexities. So that is all taken care by the OS. So we have a device driver which takes the instructions by the OS and conveys it to the device in its own language or in the way it is able to understand. IO subsystem is responsible for memory management of IO, and here buffering is provided. So buffering is a portion of memory which is provided to compensate the speed disparity between the device and the computer. So that is elaborated in the buffering topic. And caching is also sometimes provided. When the same content is referred more than once, the time can be saved by storing it in a temporary area called caching. But this caching is different from the cache memory. That cache memory is between main memory and the CPU. But what we are talking about, a memory which is allocated in the secondary storage, acting as a caching. And spooling is the overlapping of output of one job with input of other jobs. So the device drivers are also provided. In the next chapter, we discussed about the operating system structures. So structure of the operating system has got these topics: services, user interface, system calls, system programs, design and implementation, virtual machines, system boot. This is the last chapter as for the first unit. So this is the services summarized. So the various services of the OS are summarized here. The first service is providing a user interface. And we know that there are three types of interfaces available: GUI, batch, and command line. So GUI is currently the predominant user interface for operating systems. The Windows based OS are examples. Command line is the older one under Unix based operating systems, or even MS DOS was command line based, and batch was much older. So when the initial computers were there, there used to be batch processing. So by the time there is a module called monitor, which was residing in the batch OS, and that was taking the request of the users. So we have got three types of interfaces to the operating systems. The next service is system calls. So system calls. Okay. Now I'm going to tell you that so far in what we have discussed, this has to be considered as the most important question. So that is, explain the types of system calls, examples of system calls, what are system calls. So you may expect a question on system calls, and that could be framed in any way, which there are different ways the question can be framed, but the basic point is that if you thoroughly prepare on system calls, you may have a chance of answering a question. This is my prediction based on experience. So I don't know whether the actual question paper is going to have or not. So system calls is a major aspect of operating system. So what are system calls? System calls are a way by which the user programs can interact with the operating system modules. See, the operating system has got a lot of very useful functionalities, like there is a fork function available within the OS through which child processes can be created. Similarly, there are IPC functions like shared memory, message passing. Those facilities are also there. Pipe is also included. So file management is also part of the OS. And even if you take the IO operations like scanf, printf, that also has to be done by the OS only. So the various activities which are only done by the operating system, if the user program wants to utilize them, then it has to make a call, and that call is called as a system call. It's a bridge between the operating system and the user applications. So this is the list elaborated. User interface, program execution has to be facilitated by the OS, which involves loading of the program into memory and then execution of the program, converting that into exe and then executing that program like ./a.out. And during the execution, it may have to go through some IO operation. It may be either involving an IO device or a file handling. And then file system manipulation is again facilitated by the OS. Another is communication, IPC. So communication, it could either be processes, it could either happen between processes running in the same system or running on systems across a network. So we have got two techniques available: shared memory communication and message passing. This is again an important topic. List out the services of operating system, and also uh, a question may be asked on IPC, inter-process communication. Explain the methods of inter-process communication, or explain shared memory based communication with the program for that, or explain message passing based program with the suitable program. So you have, and the next one is error detection. So errors are happening at the different reasons and also different mediums. Like an error can happen on the CPU, memory, IO devices, or in a user program. When an error happen in a user program, we call it as a exception or a trap. So hardware errors or software errors, both are possible. So the OS has to take an appropriate action to deal with the error, and that appropriate action may even be terminating the process. It may even have to kill the process if that is the only option left. Otherwise, it will try to notify to the user that something abnormal has happened in the computer. We get to see some notification like that when something goes wrong. So another is debugging facility that is also provided to the programmer. Next is resource allocation. So allocation of resources, when many users or many processes have to share resources, resource conflicts are likely to happen. So another in a separate unit, we will discuss synchronization and what are the potential problems associated with the concurrent processes. So right now, we just look at the resource allocation as the responsibility of the OS. So many types of resources are available, like the CPU, main memory, IO devices, files. So all these are managed by the OS, and also keeping track of the user statistics, accounting is also by the OS. Protection and security is about ensuring that the different users do not violate their boundaries, and authentication is also done. That is, the user has to have some user ID or password or biometric based information to decide, for the OS to decide whether it's a authorized user or is a unauthorized user. Now system calls. So system calls are the programming interface to the services provided by the OS, and they are typically written in high level languages. And okay, now the role of API is highlighted here. See, normally system calls are implemented within the OS and the user program has to access. But generally, does not happen directly. That is, the user programs don't generally make a direct call to the OS modules. Instead, they use a kind of connector called API. So API is like a interface between the user program and the OS modules. The reason that why we use an API in between the user program and the operating system is actually listed as the last point in the slide. So the three most common APIs are Windows 32 API for Windows based systems, POSIX API for all the POSIX based systems like the Unix, Linux, Mac, everything, and Java API specifically for Java environment, Java virtual machine. Now the question is, why APIs are necessary instead of direct system calls? It is for these two reasons. One is portability. If you allow the programming language to directly interact with the OS, it will become OS dependent. The code that is developed in the program will be OS dependent or platform dependent. So when you make it API based, then it becomes independent of the OS. So by changing the API definition, the same program can work seamlessly with any OS. So portability it becomes available because of the APIs. Secondly, simplicity. So you don't need to expose the complexity of the system calls to the user programs or the user programmer. So that is simplified when there are ready-made APIs provided. This is an example of how this happens. This example is about a printf. So whenever you write a C program which has a printf function call, what really happens behind is that this printf is connected to a system call called write function. So the write is actually the system call within the OS which has the necessary functionality needed by the printf, which is displaying some string on the monitor. So the printf is not capable of on its own, it's not capable of writing on the monitor, but it is making use of a ready-made or built-in function system call called write. So it is invoked. And there is also modes which happens as which I have already mentioned. So whenever the system calls are executed, the operating system turns the system from user mode to kernel mode and then completes the required system call. And we have come across the various examples of the system calls. Please go through that before the exam. As I told you, the system call is a very important topic. So you may be asked to explain the system calls. In that, mentioning the examples is implicit. Even if the question doesn't mention explicitly that you give some examples, you always are expected to mention the examples. So just go through the various examples you have in the book. The next similar idea is system programs. System programs are programs that are helpful for hiding the hardware complexities like device drivers. So they provide a convenient environment for program development execution. Some of them are simply user interfaces to system calls, and others are considerably more complex. We have system programs for file handling. There is a DBMS, for example, DBMS or RDBMS. They are examples of the system programs. And status information. Some ask the system for info like date, time, amount of available memory. For that, we need system programs. Even a compiler is a system program. And these are various other examples. So compilers, assemblers, debuggers, interpreter, loader, linker. So the list goes on. So allow users to send messages to, okay, this is about a particular communication, it seems. The next is operating system design and implementation. So the operating system design is a very complex task. It involves step-by-step implementation. Following the various steps properly leads to a successful OS design. You first start by defining the goals and specification. That is a first task. That is identifying the goals of the OS and also the specifications. The goals may be classified into two types: user goals and system goals. User goals are OS should be convenient to user, easy to learn, reliable, safe and fast. Whereas system goals are related to efficiency. OS should be easy to design, implement and maintain, as well as flexible, reliable, error-free and efficient. So these are two classifications of system goals. And then the policy. So there are two points like policy and mechanism. Policy is what will be done. Mechanism is how to do it. Okay, another very important topic which I would like to tell you is the topic of operating system structure. So again, you note it as an important question in the first unit. So you may be asked to explain the simple structure, layered architecture, microkernel architecture, and loadable kernel. Yeah, four types of operating system structure. So you may be asked to explain the four types or different types of operating system structure. So the first structure is called a simple structure. Simple structure is in fact unstructured. So the initial OS, they were simply written as a single large programs. They were not separated or divided in any way. They were just running as a single large program like Unix or MS-DOS, unstructured. or unorganized. And the reason is mentioned here why people had implemented such operating systems is that basically they were not actually planning to implement an actual OS. So if you take MS-DOS, MS-DOS I guess was implemented by Bill Gates during his initial days. It's only after the success of the DOS operating system, the company of Microsoft started to grow. So that by the time it was implemented more like a passion. The person has got some passion in coding, and he started writing an OS in, simply it's just out of his passion or hobby. But it resulted in a successful product. So as a result, it was not well structured. Another reason that is also available here for this problem is that lack of hardware support. So we have seen that the dual mode operation is very crucial for the protection of the computer, but that requires the hardware support. So only if you have a register which has a mode bit, you can differentiate the different modes. But by the time the hardware, that is the processor, did not have that option, so there was no structuring provided in the OS. And as a result, the limitation is that the OS allowed the user application to directly manipulate the hardware. That is, there were no system calls. There were no system calls available. So from your program, you can directly manipulate the computer hardware, and that could result in serious attacks. That was the drawback of the unstructured or the MS-DOS like kind of system operating systems. And the next is example is Unix. So Unix also very similar, but it's slightly better. Here there were two divisions. One is the system programs and the kernel. So it consists of everything below the system call interface and above the physical hardware is kernel, and it provides the file system, CPU scheduling, memory management, and other functions. But it is also a simple structure where there were no layers available. A single kernel is running, and the kernel always runs in kernel mode under the first category of simple structures. And this is the model of that. The next structuring was a layered approach. The layered is like divide and conquer. So here people recognized that running this entire OS as a single module is not actually good. So it is having a lot of problems like so for everything you have to make a kernel switch. So whatever the requirement of the user process, everything has to be fulfilled by the OS, which means that the user program will be preempted very often due to the switch from user mode to kernel mode, and then this will delay it's like driving the vehicle on a heavily uh, road that has got a more number of speed breakers. So that is the drawback, and layered approach to overcome that. So here the operating system is subdivided into number of layers. And another advantage is that when a layer needs to be updated or modified, it need not require the entire OS to be updated. That is, you don't need to recompile and replace the entire OS. You just have to modify a particular layer which needs to be modified. So that is the advantage of the layering architecture. And layering architecture involved message passing. This is the point you are expected to have in your paper if this question is asked. So between layers, if communication has to happen, it involved a message passing as a mechanism. The next one is microkernel architecture. So okay, I think I was wrong. Microkernel architecture actually needed message passing. So here the communication takes place between user modules, so using message passing. The benefits are easier to extend microkernel, easier to port to the OS to new architecture. It's more reliable and more secure. And determinants performance overhead of user space to kernel space communication. Okay, I think I have to point out the difference between the layered approach and the microkernel. So, see, microkernel architecture or microkernel structure is very close to the layered approach, because in both cases we break the OS into smaller partitions uh, called layers. But what additionally happened in microkernel architecture is that the kernel size is reduced, which means that out of the various modules of the kernel, some of them which are not so crucial, they were taken out of the kernel and they were simply made to run in the user space. So everything is not in part of the kernel. It's like, for example, uh, there is an institution where the particular principal may have a policy that for everything he is the one who has to authorize. So for every letter by the student, it has to come to the principal, and principal will decide the whether it has to be approved or not. In another structure, the principal gives a lot of responsibility to the teachers. So for some of the requirements that students can resolve or get it done at the teacher level, only for certain limited requirements they have to approach the principal. So layered approach is like the first model where everything is uh, taken care by the principal. But microkernel is that some aspects are left to the user of processes. Only a limited requirements have to be are kept within the retained in the kernel. Now the ultimate advantage of the microkernel architecture is that number one, the kernel becomes smaller. So the size of the kernel becomes smaller, and the number of system calls or the mode switch becomes reduced, because everything need not go to the OS. So the number of mode switch will be gets reduced. Loadable kernel takes it to one more level. That is, you can even avoid the loading of the kernel modules when they are not needed. So dynamically you can load and integrate the modules of the OS. So that is dynamic. It's more dynamic. At runtime, you can bring some new modules and integrate them with the existing modules. And also, it does not involve the message passing, which was mentioned in the previous one. This is the idea. So this is the model of the Solaris loadable kernel architecture. So initially there is only the core kernel, and these are all attached. So as and when the need arises, they can be dynamically linked. And the ultimate structure of the operating system nowadays is virtual machines. The virtual machine model takes a completely different way. It virtualizes the computer entirely. Like there is a virtual hardware, there is virtual OS. So a single computer can run multiple OS, and the OS, different OS may have a different view of the hardware. So how much of memory is available, what is the processing capability, that is all virtualized. So it is a illusion. The operating system, the host operating system creates an illusion about the hardware facility. And we have got two types of OS. One is host OS and guest OS. Host OS is the actual OS controlling the computer, and guest OS is the OS that is running on with the help of the hypervisor. So hypervisor is the virtualizer software which facilitates the creation of the virtual machines. This idea is actually termed as virtualization. It's a very I mean important topic. You have to spend some additional time to learn the idea of this topic. So we have the hypervisor. With the help of it, we can run three different OS. But in a non-hypervised environment, you can have only one OS at a time. A good example why this could be helpful is that, take the example that, for example, there is a company which has a older computer which is running, let's say, a Windows OS or Linux OS or Unix or something, and they are running their applications on top of the OS. But suddenly they want to run a new application, but it's not compatible with the the OS that they are having in the computer. So as a result, they have two choices. One is either to avoid the usage of that particular application, or to replace the computer, or to buy a new computer with the necessary OS. But now what happens is that you can retain the same computer with the original OS. You just have to install a hypervisor, and then you can run any other OS on top of that. So this is a major advantage which saves a lot of money for the company. So VMware is a very popular the virtualization tool. Java virtual machine is also based on the same principle. So the last topic is booting of a computer. The simple idea is that whenever you turn on your computer for the first time, it takes certain steps for the computer to get started. That is, initially the RAM is blank because it's a volatile memory. So there is no OS running in the computer. So the objective of booting is to load the OS into the main memory. And that happens in the following steps. That is, first the computer starts the power on self test. There it checks whether the basic hardwares are all connected. Hardware means the keyboard is connected, mouse is connected, monitor. So it checks whether the hardware is properly running. Secondly, it loads the BIOS. So BIOS is a set of files that comprise of the basic input output sequence, and then it may be by password protected if needed. And then the BIOS makes a call to the MBR, master boot record. The master boot record is the one that is capable of loading the OS. So MBR points to the boot record of the selected operating system. The booting hardware may be either hard disk, or it may be CD drive, or it may be some USB drive. So according to the setting of the BIOS, it's either available in any of the secondary storage devices. So accordingly, the OS is located and it is loaded into the computer memory. Once the OS enters into the main memory, it takes control of the system. This is the sequence of events that happen during the booting. These are all the points we discussed under the first unit, which gave a kind of overview